So welcome back to this series of 2 video tutorials based on the Siemens Simcenter Testlab modal analysis tutorial that we've been looking at. And we've been looking at modal analysis of a simple plate-like structure made in acrylic or plexiglass material. Previously, we had a look at the project file that's been provided for us. We looked at the FRF sets, we looked at the geometry, we worked through modal analysis, had a look at some of the functionalities in Simcenter Testlab, and we left off having completed this animation from the Navigator workbook. And I want to pick up the tutorial at essentially sections 5 and 6. We've had a look forwards really with the Navigator at what's included in section 7, but we didn't yet look at modal synthesis and modal validation. So that's the purpose of today's exercise. If we move into the modal synthesis workbook here are my various processings. The one that was provided with the file as I inherited it, and my time MDOF processing, where I identified 6 natural frequencies, and the Polymax processing, where I identified a 7th natural frequency. And you can see that the processing that was done before also had 7 frequencies identified within that 100 Hertz approximately to 600 Hertz band. Here you can see the frequency range that we worked with, or that was worked within in the processing example, and my Polymax example has a similar frequency band. The purpose of this particular workbook is to allow us to compare and contrast the mathematically fitted data to our experimental results that are being used to animate the shapes that we're reporting when we do an experimental modal analysis. And this is a very important part of the process. It's no good just producing mode shapes and hoping that they are valid and then reporting them without understanding what's happening to produce those results. And so these are the mathematical models that have been fit as part of our picking of poles within the stability diagram, and this is the result. So you can see here that we have, like, I've selected all of these 7 modes plus the upper and lower residuals. The upper and lower residuals, by the way, are the bits that we need to include at the upper part and the lower part of the band, or the FRF band, that represent anything that's happening below here, rigid body modes, or if we've chosen a different band, we might have some dynamic modes that we deliberately ignored. And similarly, above this upper band, we will always have more modes that have been ignored. And so the lower and upper residuals represent the contributions from modes outside of our band. And we can scroll through the various FRFs here to compare and contrast. So if left side is one shaker, right side is another shaker in 2 different corners of the plate, and you can see the comparison. We're looking at the correlation, and we're looking at the error, and we're looking at the fit generally, and is it good? In this case, we have nice clean FRFs. It's relatively easy to fit mathematical data to the experimentally captured data. You can see we have an amplitude and a phase, and the frequencies, the natural frequencies, have been included with these cursors as well for us. So you can see here there are 7 frequencies. Remember that those are from the Polymax processing, these 2 close modes here, and also we have these very 2 close modes here. As well as having a peak in resonance, we also have a shift through 180 degrees in phase when we go through a resonance, and an anti-resonance, as you can see here. So these are the things that we expect to see in a frequency response function. And I can scroll through these one pair by pair if I hit this automate button here, or I can manually move through them here more quickly. This one will still be playing, but you can see what's happening as I scroll through. It's quite interesting with these data. When we look at some of these particular frequencies, we don't see a resonance at all. And look at also this pair here at point number 8, which is right in the middle of the structure. Yeah, there's no features here or here, no resonances, and nothing here at 305 Hertz. Let's think about why that is. Right? When we did quadrature peak picking, just using FRFs and looking at the imaginary part, extracting the value of the imaginary part at the peak, and using that to plot for each of the frequencies the levels of vibration of the points on the structure. This is exactly the same process essentially that we're going through here with modal analysis in a commercially available system. You can think of it in the same way. So if we look at the shapes, remind ourselves at 305 Hertz, what was that shape look like? So here we can go back to our navigator. We can pick that mode, drag it and drop it in here. And here you can see this particular mode has got very, very little motion along this central region here. It's all, because it's the the second torsional mode, it's all dominated by motion along these edges and nothing along the middle. And that's what these data show us. Yeah, we can see here, let's change back to those two, that there's very little motion here. And the noise here is quite high. Of course, our mathematical model doesn't include the noise, and that makes it easy for us to differentiate. The green curve is the mathematical fit, the red curve is the data, and there's some quite relatively looking high noise, but we're really focused on these resonant frequency locations. Okay, so we keep scrolling through, keeping an eye on these things. Let's have a look at some other features. Here you can see an example of a phase wrap. Another phase wrap here. You might have seen this from time to time as we've worked through these FRFs. This is just the phase wrapping through 2 pi radians. Phase can only take a value, of course, between minus pi and plus pi, but sometimes it will go lower than minus pi, which is essentially the same as being just under pi, and that's what a phase wrap is. We see a phase wrap if we pass through an anti-resonance or a resonance. So we work through these. Here's some more phase wraps. We're looking at very strong correlations and very low errors, as that's what we would expect from this kind of a clean looking data set. Real world data sets will be potentially more erroneous, and we have to take care when testing real world structures, not just simple plates, that we have high correlation. We can also just look at a particular mode by mode individually, rather than looking at the whole set of modes in the data set. And when you do that, you can also get an idea about what's going on in the analysis. Essentially, these modes are a single degree of freedom system, right? So for each one of these, we have a single degree of freedom system. As you can see, this is a characteristic single degree of freedom system, one peak. And it's essentially the summation of these that leads us to the full mathematical model. And when I add them all together, we've got, this is the outcome. That's what's happening. So that's also quite interesting to look at. That's modal synthesis. Let's have another look, or a quick look now, also at modal validation, which is an equally important part. Here we've been looking at the FRFs, the raw data against the synthesized FRFs. Next, we should look at the mode shapes for the processing and compare and contrast then. So here we are in the modal validation workbook, and some features in here, right? We can choose which processing we're interested in here. So there's the original processing. There's the second. Here's my Polymax processing. And the first thing that I can do is come in here and I can run an AutoMac. So I push this button here and I get an AutoMac, a modal assurance criterion. And this essentially provides us with a matrix which is comparing mode 1 with respect to mode 2. Mode 1 with respect to mode 3, mode 1 with respect to mode 4, and so on and so forth. Of course, this is an AutoMac, so we're comparing this processing with itself. If there were some off-diagonal terms that had some high values, that would mean that there was significant similarity in the mode shapes, and that might indicate that we'd either missed a mode or we'd inadvertently selected a wrong mode in the stability diagram when we were doing our peak picking. And I can demonstrate that quite nicely by looking at this processing, which I did in time MDOF, where I selected fewer modes than there were available within the processing. So remember that the processing has got 7 frequencies, as has the Polymax processing, but my processing has only got 6. And then you can see exactly the issue here now when we compare. Instead of an AutoMac, we do a modal assurance criterion between what's being viewed here. So we'll choose this one, and the original processing from the project that was. So rather than doing an AutoMac looking at it against itself, we're comparing one against the other now. And so I only have 6 modes across the top. That's my processing, and the original processing included with the project is 7 modes. These numbers look okay, they're close to 100, but here we have 2 high values, two lower than 100 values, right? We have off diagonal terms here because these 2 modes are different to one another. They're not, essentially, we're not comparing apples with apples anymore. If I instead look at my Polymax, where I have 7 modes identified, and compare that with the original processing, Now you can see we have the same number of modes and there's limited off-diagonal terms, very small off-diagonal terms. I can compare and contrast different modes with one another also for the original processing. So I need to select this one in the display. So let me choose to display this one on the left-hand side. Let me go to the original processing and display that one on the right-hand side. And as you can see, we get good comparisons just looking at them visually, and I can scroll through them. Now taking the next mode from my processing and comparing it against the processing that was included with the project. And so that is a very strong comparison. And that's why we see what we see in this modal and assurance criterion matrix. We can also have a look at the complexity of the modes. These should all be real normal modes. For a simple structure that behaves linearly like a flat plate, we expect to find these mode shapes to be what are referred to as real normal modes. That means there's no complexity. We have a very high modal phase collinearity value, near 100%, these are in percentages, and a low mean phase deviation. So we get that information from the compact mode complexity plots. And there are a whole range of other functionalities and features in here that we can make use of. We can compare, in this case, we're now comparing the same thing with itself. So we get the same there as essentially if we've done an AutoMac. But if I compare this processing with the original one, the new Polymax one, then I get to be able to produce a very nice table that shows me frequency A versus frequency B and the deviation in hertz, damping A, damping B, deviation is a percentage. The mean phase the modal phase collinearity value compared against one another, and the MAC values to the comparison between one and the other shape. So that's, I think, now completed the tutorial exercise. As I mentioned, there are very many more advanced features within this kind of capability that are beyond the scope of this subject, but you might be interested to explore those in further detail. I hope that's been helpful and a bit shorter video than before. Thank you.